Look at your phone, your tablet, your laptop, your car dashboard, your ATM. What do they all have in common? A touchscreen. It feels simple. You touch the glass. Something happens. But beneath that smooth surface is complex engineering, multiple technologies, and decades of innovation. In this video, we're explaining every major type of touchscreen, how they work, why they exist, and where they're used. By the end, you'll understand what actually happens the moment your finger meets the screen. Let's start with the basics. A touchscreen is an input device layered on top of a display. It detects touch and translates that physical interaction into digital signals. But not all touchscreens work the same way. Different technologies were developed for different purposes. Some respond to pressure. Some respond to electricity. Some respond to sound waves. Some don't even require direct contact. Let's go through them one by one. The first major type is the resistive touchscreen. Resistive touchscreens were widely used in early smartphones, GPS devices, and industrial equipment. They work using pressure. Inside a resistive touchscreen are two thin, flexible layers coated with a conductive material. These layers are separated by tiny spacer dots. When you press the screen, the top layer bends and touches the bottom layer. This contact changes the electrical current at that specific point. The device calculates the coordinates and registers a touch. Resistive screens can be used with a finger, a stylus, gloves, or almost any object. But they have downsides. They are less responsive. They don't support multi-touch easily. And image clarity is slightly reduced due to the extra layers. Next is the most common type today, the capacitive touchscreen. Capacitive screens respond to electrical properties of the human body. Your body naturally conducts electricity. A capacitive screen has a transparent conductive layer, usually made from indium tin oxide. When your finger touches the screen, it disturbs the electrostatic field at that point. Sensors detect this change and calculate the touch location. Capacitive screens are more responsive. They support multi-touch gestures. They offer better clarity, but they usually require skin contact or a special stylus. Regular gloves won't work unless designed for touchscreens. There are two main types of capacitive touchscreens: surface capacitive and projected capacitive. Surface capacitive uses a uniform conductive coating across the screen. Projected capacitive, or PCAP, uses a grid of electrodes embedded within the glass. Projected capacitive is what most modern smartphones use. It allows precise multi-touch tracking and works through thicker glass layers. That's why modern screens feel smooth and accurate. Now let's talk about infrared touchscreens. Infrared touchscreens don't rely on pressure or electrical conductivity. Instead, they use a grid of invisible infrared light beams across the surface. Sensors line the edges of the screen. When a finger interrupts the light beams, the system detects the position. Infrared screens are durable and don't require physical pressure. They're often used in large displays, kiosks, and interactive boards. Because they don't need a layered film, image clarity remains high. However, dust or debris can interfere with accuracy. Next is surface acoustic wave technology. Surface acoustic wave screens use ultrasonic waves that travel across the surface of the glass. Transducers generate sound waves, and receivers detect them. When you touch the screen, you absorb part of the wave. This disruption is measured and converted into coordinates. These screens provide excellent image clarity and durability. They're often found in kiosks and information terminals. However, they can struggle in dirty or wet environments. Now let's explore optical touchscreens. Optical touchscreens use cameras placed at the edges of the screen. These cameras detect shadows or reflections caused by touch. Advanced algorithms determine the exact touch point. Optical systems are common in large interactive displays and collaborative screens. They allow multi-touch and stylus input without special coatings. Next, let's talk about resistive versus capacitive in real-world usage. Resistive screens are ideal for environments where gloves are necessary, like factories or hospitals. Capacitive screens are ideal for consumer electronics, where responsiveness and gesture control matter. That's why smartphones universally use capacitive technology. Now let's move to modern enhancements. Multi-touch changed everything. Early touchscreens only detected one point of contact. Modern projected capacitive screens can detect multiple touch points simultaneously. This allows pinch to zoom, two-finger scrolling, complex gestures. Without multi-touch, modern interfaces wouldn't exist. Next is force sensing. Some devices introduced pressure-sensitive touch, where the screen detects not just location, but how hard you press. This allowed different actions depending on pressure level. Although not widely adopted long-term, it demonstrated how touchscreens could evolve beyond simple taps. Now let's talk about haptic feedback. Touchscreens are flat and smooth. They lack physical buttons. Haptic feedback simulates the feeling of pressing something through vibration. This creates a more tactile experience. Next is stylus technology. Capacitive styluses mimic the electrical properties of a finger. Advanced styluses include active components. They communicate directly with the screen for pressure sensitivity and palm rejection. This is essential for digital artists and note-taking. Now let's talk about durability. Modern touchscreens use strengthened glass. Scratch resistance, impact resistance, and chemical durability are critical. Beneath the glass are multiple layers. Protective glass, touch digitizer, display panel, backlight or OLED layer. Each layer serves a purpose. Touchscreens are not just glass panels. They are layered systems engineered for clarity and durability. Now let's discuss foldable touchscreens. Foldable devices use flexible OLED displays combined with flexible touch sensors. The challenge is maintaining sensitivity while allowing repeated bending. This required new materials and new engineering techniques. Next is in-display fingerprint sensors. Some screens now include biometric sensors beneath the glass. Optical sensors use light to scan fingerprints. Ultrasonic sensors use sound waves for 3D mapping. Touchscreens are no longer just input surfaces. They are integrated with security systems. Now let's look at large-scale touchscreens. Interactive whiteboards, digital kiosks, self-checkout systems. These often use infrared or optical systems due to size. Scaling capacitive technology to very large surfaces is complex and expensive. Now consider automotive touchscreens. Car displays must handle temperature extremes, vibration, and sunlight. They often use specialized capacitive layers with anti-glare coatings. Touchscreen design changes based on environment. Now let's talk about why physical buttons are disappearing. Touchscreens allow dynamic interfaces. Buttons can change based on context. Layouts can update through software. This flexibility makes devices more adaptable. But there are trade-offs. Touchscreens lack tactile certainty. You must look at the screen to interact. Physical buttons provide feedback without visual confirmation. This is why some industries still rely on physical controls. Now let's talk about the future. Researchers are developing touchscreens that simulate texture. Electrostatic friction can create the illusion of roughness. Ultrasonic vibration can simulate button clicks. Some experimental screens detect gestures above the surface without direct contact. Touchless interaction may become more common. Artificial intelligence will also play a role. Screens may adapt sensitivity based on user behavior. They may distinguish between intentional and accidental touches more effectively. The touchscreen has evolved from a novelty to a universal interface. From resistive pressure-based systems to advanced capacitive multi-touch grids. From simple taps to complex gesture ecosystems. Every time you swipe, pinch, or tap, a series of electrical calculations happens in milliseconds. It feels instant. But behind that instant response is decades of innovation. Touchscreens didn't just replace buttons. They reshaped how humans interact with technology.